Hey Keme, this is Miss Mac. Obviously, I'm not at school today, but we're gonna do the review for your test, anyways, as if I was there. And I'm pretty pumped because I get to use my wipe off board that looks like a periodic table. So get pumped. All right. Hopefully, you guys already have your chapter reviews out. Just real quickly, I want to run through what you're allowed to have on your cheat sheet. Okay. So that's your periodic table that I gave you on Friday. You're allowed to have a lot of stuff on it. So starting with just kind of that first, that kind of number one and number two of what you're allowed to have. Your periodic table should look something like this for those first two. So it says you're allowed to have your group numbers and your group names on there. This is not flipped. Hold on. Let me see if I can't flip. It might flip it on its own. Never mind. All right. So you're allowed to have group numbers, group names, and you're allowed to have a note to yourself that the group number is equal to the number of valence shell electrons on that atom. Okay, so those are the electrons that are in that highest energy level. All right. Remember, there's one exception to this. It's helium. All right, helium, even though it's in group 8A, it only has 2 valence electrons, so just kind of watch out for that one. All right, but you can have your alkali metals, your alkaline earth metals, your halogens, your noble gases, your transition metals, and your intertransition metals all labeled on there. Okay, so that's kind of that first set of things you're allowed to have. Okay, so the next couple ones on your cheat sheets talk about, for number 3, they say that you can have the charges on your periodic table. So what that means is that above each of the group numbers, you can have the charge that normally those elements in that group would have if they form ions. So like, for example, group 1A will always form ions with a 1+ charge. Group 2A, 2+, group 3A, 3+. Don't forget what it means to have something that's positively charged. So if it's positively charged, it actually means that it lost electrons, not that it gained something. So positive charge means you have more protons than electrons, so you must have lost electrons. Group 5A and 6A and 7A, those are your negatively charged ones. So those are the ones that actually gained the electrons. Group 4A, you don't need to worry about. The transition metals, you guys don't need to worry about. And your noble gases, remember, the whole reason that anyone forms an ion, whether it's positive or negative, is because everyone's trying to look like a noble gas. So if you're already a noble gas, you're not going to form ions, you're not going to bond with anything. So for your noble gases, you can have a 0 up there, but really you just need to know that it doesn't form ions. You can also have the summary table that we kind of created once we went over the ionic size trend across a period. Remember, there's a few things kind of going on when you lose and when you gain. So all of your positive ions are always going to be smaller than the negative ones in the same period. All right, so you can kind of draw that summary chart that we did together in class. Okay, next up for item number 4, it says you can do your labels for electron configurations. All right, so what that means basically is that you can label your periodic table with the S, P, D, and F blocks. All right, so whether that means they're chunked off or you just have a note to yourself somewhere which block goes where, you can have those labeled kind of like what I did here. And you can also label like the periods, like going down, like 1, 2, 3, 4, 5, 6, 7, saying that it says what energy level you're in. But for this test, you're not actually going to need that. Remember, you're not allowed to actually draw the chart that has like 1s2, 2s2, 2p6. You're not allowed to actually have that chart on there. So make sure that you don't do that. Okay? All right, that's pretty much it with that one. Oh, just kidding. I forgot to say why this is important. So hopefully you guys remember, but the S, P, D, and F blocks, the reason we label them that way is because that's actually the sublevel that the last part of the electron configuration is going to be in. So like for example, if you look at something like fluorine is in the P block. So when we do its electron configuration, we have something like 1s2, 2s2, 2p5. So you'll notice the last part is 2p5. So the last part of electron configuration is in the p sublevel. Right, so that's why we label those blocks that way. All right, so real quickly, let's kind of go over periodic trends, what you're allowed to have on your table. You can have any kind of way you want to summarize it, but for atomic size and ionic size, you want to say something about how they increase going down the periodic table, whereas ionization energy and electronegativity decrease going down the periodic table. You want to say something that for atomic size, it actually decreases as you go across the periodic table, and ionization energy and electronegativity actually do the opposite, and they increase going across the periodic table. So again, you can kind of decide how you want to do that, but something like this is one idea. You can have it actually on the sides. I just don't have room on this board for that. Remember that atomic size and ionization energy are exact opposites of one another, and electronegativity and ionization energy are almost exactly the same, other than for the noble gases, they have the highest ionization energy, but they actually have the lowest, or actually no, electronegativity. Okay, so another way of kind of remembering that, if you don't think you'll remember to do that, is to just write on your periodic table that fluorine is the most electronegative element, and then you won't have to remember that, and that kind of helps. All right, one last thing you can also have on your periodic table is you can and should draw the stair step. All right, remember it starts in between boron and aluminum, and then you go over one, down one, over one, down one, until you get to the bottom of your periodic table. Any element that has at least one side touching the stair step is going to be a metalloid. The only exception to that is aluminum. Even though aluminum's touching the stair step, we actually consider it a metal, but I think that's a pretty easy exception for you guys to remember. Anything then that falls on the, left side, on the left side of the periodic table, or the left side of the stair step, I guess, is going to be your metals. Anything on the right side then is going to be your nonmetals. There is that other, one exception as usual. Hydrogen, even though it's over on the metal side, it is a nonmetal, so don't forget that. All right. Also, don't forget that it's, even more of an exception because it's in group 1A. Remember, group 1A are the alkali metals, but we don't want to say that hydrogen's an alkali metal because it's a nonmetal actually. All right, so just don't forget that. Okay, so that was kind of our quick recap of cheat sheet. So make sure that yours follows all the rules. You don't have things like definitions or like reasons why the trends happen. We'll talk about some of those now, but that's not allowed on your periodic table. Okay, just the stuff that you saw on the awesome wipe off board. Those are the only things you're allowed to have on your periodic table. Okay. Now, if you have your reviews out still, all right, we're just going to kind of run through some of the answers to the questions. I left the answer key with the substitute who's there, so just in case anyone has any questions, you can also ask them. But I'm going to run through the answers just real quickly, so that should help as well. Okay, so number 1 asks, how is atomic size measured? All right, hopefully you guys already know this, but we do it with the atomic radius, all right? But instead of measuring from the distance of the nucleus to the outside of the atom, remember there's electrons out here on the outside, and we can't really tell where those are. So we actually measure atomic radius by having 2 atoms of the same element bonded together, and we take the nuclei of one and the nuclei of the other, and we say halfway in between there, the distance from one nuclei to that distance halfway in between is the atomic radius. All right, so there you go. All right, number 2 asks, why does the atomic size then increase when you move down a group? and why does it decrease when you move across? So this is one of those reasons why. So this is something you're not allowed to have on your periodic table. For all of these trends, the reasons why it's going to do anything as you move down a group is because you're always adding an energy level. So every time you move down a period, all right, or you start moving down on a group, you're going to be adding energy levels, all right? So you're getting bigger. It's like adding more shells to your outside layer, all right? When you go across a period on the periodic table, you're going to have the same number of energy levels, but a stronger nucleus, so like that more positive nuclear charge. So it's going to actually kind of be a more positive charge, which is going to bring those electrons in tighter and tighter and tighter. So even though it's not a huge change in their size, it's still going to affect it and make it go just get a little bit smaller when you move across the periodic table. Okay, so that pretty much sums up atomic size. Ionization energy was the next one. So ionization energy is the amount of energy it takes to remove an electron. So take an electron from an atom. Right? So the amount of energy required to make it basically like a positive ion. So if you're removing an electron, you're making it positive. So a lot of our metals, like group 1 and group 2, they actually want their electrons to be taken. So it's pretty easy to take those electrons versus something like on the other side of the periodic table, we have things that normally want to gain electrons. They're going to have really high ionization energies because it's going to take a lot of energy in order to remove their electrons, especially like a noble gas. All right, so when it asks you in number 4, what specific group of elements has the highest ionization energy, it's going to be higher the more you go to the right of the periodic table. All right, so your noble gases, group 8A, that's going to be the highest ionization energy because they don't want to change the number of electrons they have. They're perfect. They don't want to change at all, so they're going to fight really hard to keep their electrons. Okay? Going on to number 5 then, why does it decrease as you move down the periodic table? That's going back to that really awkward kind of analogy I talked about, where when you go down the periodic table, we have that shielding effect. And so that shielding effect is basically saying the more energy levels you have these electrons that are on the inside that are kind of blocking the nucleus from really attracting those outside electrons. So we talked about it when we said something like hydrogen only has 1 electron and 1 proton. So they're right next to each other. It's really hard to steal an electron from something like hydrogen. Whereas if you keep going down, you get to things like sodium or potassium. Now they have a lot more electrons that they're taking care of. It's a lot easier to steal an electron for those ones, okay, because that electron is so much farther away from the nucleus, okay? So that's kind of that explanation for number 5, all right? Again, number 6, the only reason we ever gain or we lose electrons is always so that we can have the same number of electrons as a noble gas. That's always the goal, all right? So we bond with things, we gain electrons, we form ions. It's all about looking like a noble gas or having the same electron configuration of a noble gas. Okay, number 7. Okay, number 7 is talking about that trend in ionic size. Remember, if you have that summary table, that's going to pretty much explain that one for you. So even though, yeah, technically ionic size decreases going across the periodic table, really what's going on is we have first like a decrease in the cations, and then we have a big jump, and then a decrease in the anions. So the biggest one is actually going to be the ion that's in like group 5A, and the smallest one is the one that's in group 3A. So it's a little bit tricky. You have to have that summary chart in front of you, and you have to know really how many electrons does this have, how many protons does it have, and use that to help you figure out ionic size. It's kind of a tough one. All right, so that's number 7. All right, number 8. All right, smaller or larger. Again, it comes back to what is a cation, what's an anion. Cations are positive, so that actually means they have more protons than electrons, which means they lost electrons. If you lose something, right, you lose some matter, all right? And in this case, you even lose an energy level, all right? You're going to get smaller. If you're an anion, it means you're actually more negative. You're gaining electrons. If you gain something, you're going to get bigger, right? So you lose something, you get smaller. You gain something, you get bigger. So that one hopefully makes kind of sense to you guys. All right. Number 9 says, what's electronegativity? All right, electronegativity, don't get it confused with ionization energy, because these two, even though the trends are really similar, like when one increases, the other increases, when one decreases, the other decreases, they aren't the same thing. So electronegativity is how able you are to attract electrons when you're bonded to something else. All right, so if you have two elements that are bonded to one another, one of them's going to usually attract electrons more than the other one, all right? And the way you tell which one's going to attract them more is based on how close they are to fluorine, all right? So if you're really close to fluorine on the periodic table, you're going to attract electrons or have a higher electronegativity than something that's really far away from fluorine, all right? The only kind of thing you got to be careful with on this one is you got to remember that the noble gases are not electronegative at all. All right, so like they're always the worst. Okay, so if you're trying to rank something as like least electronegative to most electronegative, the noble gas is always going to be the least electronegative, because noble gases don't even bond with anything. So if you don't bond with something, then you can't attract electrons in a bond. All right, you like can't do it if you aren't even bonded to anything. Okay, so keep that in mind. Don't forget that. All right. Number 10 and 11 kind of talk about what I just said. So again, fluorine's the most electronegative because again, it has that strong nuclear charge. When you go across the periodic table, you have strong nuclear charges. And it doesn't have that shielding effect that we get when we go down the periodic table. So when you go down the periodic table, you have that shielding, that blocking the nucleus of all those electrons from the energy levels. So fluorine doesn't have that. So it's the most electronegative. Noble gases don't bond, so that's why they aren't electronegative at all. And so what I just kind of want you guys to take away from this kind of review is that in terms of the explanations for trends, all right, for the explanations for all of them, all right, the reason why anything happens when you go down a group, it's always because you're adding energy levels. It has something to do with that. So if you're asked for an explanation and you say there's more energy levels when you go down, then there you go. That's going to get you those points, all right? When you go across the periodic table, all right, it's going to ask you, why does this happen when you go across the periodic table from left to right? The reason is always the same. It has to do with that strong nuclear charge. So your nucleus is getting stronger when you go across the periodic table. And so if you just know that, then that's going to at least get you by on the test, all right? So make sure you know your vocab, make sure you know your definitions, but for those reasons why, those will get you by. All right, so good luck. You guys are going to do awesome on your tests, and I hope this helped. And I'm sorry I couldn't be there today. All right, have a good day, you guys.